In section 9.9, we're going to work with modeling relationships, and we're going to compare different representations of functions. The key vocabulary here is what is a verbal model, which we've talked about all semester long, slope, which you know is related to linear functions, and also the vertex, which is related to quadratic functions, as these can be really important parts of understanding basically word problems. So if we take a look at one of the techniques we might use to understand a situation would be to sketch a graph. So in this particular case, we're talking about the water from a water cannon on a firefighting boat reaches a maximum height of 25 feet and travels a horizontal distance of about 140 feet. What type of function would we use to represent and sketch the graph? So when we think about it, let's look at that. Let's say it's 5, 10, 15, 20, 25 feet. And over here, 5, 10, so this is 25 feet. 10, 20, 30, 40, 50, 60, 70, 80, 90. Here's 100 feet. And then we have 10, 20, 30, 40. So here's 140 feet. So we know that the water's going to start from wherever the height of the boat is it's not going to be right on the water level. It's going to be the boat gunnels will be above the water line, the gun will be above that. And we know that it's going to hit the water here at 140 feet. And it's going to peak somewhere in the middle. Let's say that's at 70 feet, 10, 20, 30, 40, 50, 60, 70. Not quite. It'd probably be a little more than that at about 25. So we know that the water's going to go in an arc. We know that gravity's going to pull the water back down. And this is going to be a quadratic function. This makes a parabola. So when we think about it, we're probably going to use a quadratic function. And what do these different things represent? Well, the y-intercept here, this is, as you remember I described, well, the gunnels will be above the water line, the gun will be above that on the boat. This is the height of the water gun, the height of the water gun above the water. And the x-intercept is how far away from the boat it is when it hits the water. Okay, so that's what those intercepts would represent. And then the maximum point, that's the highest, that's the peak of the arc that the water makes as it goes from the boat to this location. Okay, if we wanted to compare properties of two linear functions, we have two young ladies who are downloading songs to their cell phones. Celia's already downloaded 14 songs to her cell phone. In the future, she intends to download 2 songs per week. Now notice they're saying linear functions. So remember that 14 is the starting situation. The starting situation is always the constant. And then, so Celia's song is going to be 2 songs per week plus the 14 she already had. Her friend Connie has 12 songs and plans to download songs based on the table below, whose playlist is growing faster. Well, if you look at 22 minus 17 is 5, 27 minus 22 is 5. She's getting 5 songs a week. And this is, all right, Celia, I can't use C and C, Celia and Connie. You can see that whose playlist is growing faster. Well, Connie's equation has the bigger slope, right? She's getting 5 songs per week. Celia's doing 2 songs per week. So even though Celia started with more songs, by the time she gets on to the first end of the first week, she's going to have 16 songs, whereas Connie's going to have 17 songs. Connie's is growing faster. If we want to compare quadratic functions, Tim threw a baseball in the air and we can model its height with this function. Matt threw a baseball in the air and this is the graph. So you can see that the height that Matt, the highest, right, which ball reached a greater height, we're really now talking about the vertex. So we're talking about maximums, okay? And you can see that it looks like Matt's, the height of Matt's ball looks like it's maybe about 19 feet. So let's take a look at Tim's and figure out what's the height of its vertex. So I know the x-coordinate of the vertex is the opposite of b, which would be 40, over 2 times a, which is negative 16. So that's going to be negative 40 over negative 32. That becomes positive. Both of these are divisible by 8, so that's 5/4 is the x-coordinate of my vertex. And then if I want to find the y-coordinate of my vertex, that's going to be negative 16 times 5/4 squared plus 40 times 5/4 plus 5. So this is going to be negative 16 times 25/16 plus, let's see, 4 goes into 40 and leaves 10, 50 plus 5. So negative 16 times 16, that's negative 1. So I'll have negative 25 plus 50 plus 5. So this will be 25 plus 5, which is 30 feet. 30 feet. Which baseball reached a greater height? Tim's baseball reached a greater height. Again, when we're talking about a maximum height, when we're talking about a quadratic model, such as throwing an object, we're talking about the y-coordinate of the vertex. Finally, taking a look at a real-world scenario. During a weekend trip riding his motorcycle, Neil plans to average 55 miles per hour. What type of a function would be good for this model? Well, if we're talking about how far he's going to go, distance is going to be equal to rate times time. So y would be equal to 55x. This is a linear model. If we were comparing him to a location, we might have a constant, but right at this moment he's starting, I guess, at his home. So if we want to sketch a graph representing the distance he will travel in terms of the number of hours that he rides, we know he'd be at 0. And then for every, for simplicity's sake, I'm going to do multiples of 55 on my axis. Right? And what we're going to do is we're going to do every time he travels further, he's going to go another 55 miles, and this is what the graph is going to look like. Right? If they want to talk about the intercepts, well, the intercepts are both at the same location. That represents both his starting distance and his starting time, which are both he's 0 miles from home at 0 hours, and that's what that means. In a different context, it might mean something else. But in this particular case, he's traveled 0 distance at 0 time.